For a long time, the semiconductor industry's primary economic engine was Moore's Law, an internal benchmark of doubling the number of devices on an integrated chip every 18 months. Broadly speaking, three engines drove these advances: semiconductor design, increasing wafer sizes, and lastly, lithography. Improvements in optical lithography techniques have been the true driving force behind producing faster and faster chips. But coming up to the new millennium, it became clear to everyone that the lithographic train of progress was breaking to a slow halt. Was there enough left in the tank for one last ride? In this video, we look back at what would have been the last optical lithography technology and why the industry failed to sign on. In the 2 decades since 1980, semiconductor lithography tools had the benefit of using wavelengths smaller than, or at least equal to, the minimum feature size of their process nodes. For instance, in 1980, the industry used G-line mercury arc lamps. These had a 435 nanometer wavelength. The leading process node at the time was the 1.5 micrometer process, corresponding to a 1500 nanometer half pitch. 1500 nanometers versus 435 nanometers. In that situation, it's like drawing thick lines with a sharp pencil. So much easier. Then, in the second half of the 1980s, the industry moved to the I-line at 365 nanometers. Again, not a problem since the leading edge process node at the time was 800 nanometers. But the pace of Moore's Law was starting to catch up on the industry. In the late 1990s, the industry switched from using lamps to excimer lasers. In 1999, the year of the Dreamcast, the industry started using 248 nanometer KrF lasers for their leading edge process node at the time, 180 nanometers. 193 nanometer ArF lithography was scheduled to come online 2 years later in 2001. But by now, Moore's Law was flying like the Millennium Falcon. In just 13 years, from 1987 to 1999, the industry's leading edge process node went from 800 nanometers to 180 nanometers. From the early 1980s, the minimum feature size on an integrated chip had basically shrank about 100 times. Then, in 1999, it became the case that the leading edge process node had a minimum feature size smaller than the most advanced lithographic wavelength. And from then on, it became much harder to push the limit on semiconductor manufacturing. At around then, the semiconductor industry was putting the finishing touches on 193 nanometer ArF laser technology, scheduled for a full launch at around 2001. But with how fast Moore's Law was compounding now, analysts predicted that the 193 nanometer lasers would be unsuitable for the 100 to 70 nanometer process nodes. Those nodes needed to come out around 2003, less than 2 years after the lasers rollout. But that was alright because help was on the way, right? By then, the industry had agreed that extreme ultraviolet lithography, or EUV, was their long-term future. The foundries wanted EUV equipment in their clean rooms for the 100 nanometer process node, just in time to replace those 193 nanometer lasers. Unfortunately, it became clear that EUV was not ready. It was a completely new technology that used mirrors instead of lenses. The EUV light source was woefully underpowered, the mirrors weren't flat enough, and there were serious defect issues. Analysts predicted that EUV wouldn't be ready until at least 2010. In actuality, it was far longer than that. So what can foundries use between 193 nanometers and EUV? That is how the idea of 157 nanometers came about. 157 was meant to be a bridge from 193 to EUV, especially during the 100 to 70 nanometer nodes, which EUV should have been available for. The difference between 193 and 157 nanometers was just 36 nanometers, but this 20% reduction represents a bigger scaling down than from 436 to 365. Furthermore, 157 nanometer lithography would use a fluorine excimer laser, and thus was presumed to be similar to the 248 and 193 nanometer lithography processes. Presumably, this would smooth out the transition since relatively little would change. Considering the daunting challenges up ahead in future nodes, some advocated for rushing this technology into clean rooms to help keep Moore's Law alive. 157 equipment would hit clean rooms in 2003, just in time for the 100 nanometer process node. But such transitions are never so easy to pull off. I want to pause here to briefly discuss with you optical lithography technology, the magical light train that took us so far over the span of 30 years. First, the lithography part, and then the optical. Lithography is a process involving three system parts: the exposure tool, the mask, and the resist. First, you coat a wafer in a photosensitive chemical called a resist or a photoresist. Then you take a master image printed on what is called a mask and send high-powered light through that mask onto that wafer. The system that does this is called the exposure tool, and inside that would be your excimer laser, crazy multi-lens optical system, and so on. The resist reacts to the light so that the chip pattern gets printed onto the wafer. After that, the pattern can then be used as a stencil for further etching processes. That's lithography in a nutshell. So why am I calling it optical lithography, and does it matter? Optical lithography is different from its next generation counterparts. It has three differentiating components. First, it uses photons. Second, its masks are transmissive photomasks, meaning that they are transparent. Third, they employ projection optics to shrink an image. The pattern on the mask is often 4 to 5 times larger than what you want to put onto the chip. This is a helpful benefit that makes the masks easier to create. Development began in 1997 with a microstepper prototype at the MIT Lincoln Laboratory. It was far smaller than a commercial system, but it was capable of patterning 80 nanometer wide lines, more than sufficient for the 100 nanometer node. As I mentioned, a lithography system's critical elements are the exposure tool, mask, and the resist. All three would need extensive re-engineering for 157. Let us start with the exposure tool, which contains the laser and the optic system. Because ordinary air easily absorbs 157 nanometer light, the entire light pathway has to be purged of air and replaced with inert nitrogen. This added substantial costs to the whole system. For the laser, industry analysts early on worried whether the 157.63 nanometer fluorine gas excimer laser could output enough power as its 248 and 193 generation peers. Surprisingly though, laser suppliers quickly caught up and started producing lasers with 10 and even 20 watts of power. They were ahead of expectations, so this was essentially considered on track. But there was one serious problem with the laser. The width of its lines were too wide. Usually, this is not a major problem. You can correct it at the optic system level with different glass materials and leveraging how they disperse light just like a pair of glasses. Unfortunately, 157 nanometer light is so easily absorbed that the optic system's designers, again our friends at Carl Zeiss, only had one option for the lens material in the whole system: crystalline calcium fluoride. Specialty glass companies like Corning and Schott started working on producing enough of this crystal at extremely high purities, and the struggle was real. Furthermore, they have to grow it in such a way to minimize what is called stress-induced birefringence. Birefringence is a fancy word that describes how light splits into two when it enters a crystal. This would scatter 157 nanometer light and reduce its contrast, resulting in image aberrations. Image aberrations are not acceptable in semiconductor manufacturing. When the crystal is deformed due to weaknesses in production, unwanted birefringence occurs. The glass companies overcame this, but in 2001, a few years into test production, they realized that the crystal inherently produced some amount of birefringence no matter how unstressed and chilled out it was. This intrinsic birefringence, as it was called, was measured at just 11.2 nanometers for each centimeter of crystal, but nevertheless was a serious issue. Zeiss and ASML engineers played with the idea of introducing a second lens material into the optic system. Barium fluoride crystals, which occurs in nature as the amusingly named Frank-Dixonite, have a similar intrinsic birefringence, but in the opposite direction. However, the supply chain was not prepared to ramp up on this new material. They were having enough headaches with calcium fluoride alone, so the idea was dropped. Eventually, the engineers discovered that the amount of intrinsic birefringence depended on the direction at which the light enters the crystal. So, they created crystal orientation pairs that cancel out each other's light distortions. For instance, one crystal lens positioned in a specific orientation, which ASML labeled as 111, needs to be paired with two 100 orientation crystal lenses. The second brother of those two 100 lenses has to be tilted 45 degrees in relation to the first. This pairing requirement had knock-on effects throughout the rest of the system, for instance in the optical lens coatings and notably in the machine's embedded software, which needed rewrites. But this crazy intrinsic birefringence compensation scheme worked. Zeiss himself would be proud. You might be wondering why the lithography industry chose this specific wavelength, 157 nanometers. The number is very significant. 193 nanometers might have been the last optical lithography technology put into mass production, but 157 is the last feasible optical lithography technology, period, and that is because of the photomask. The mask is the semi-transparent template that holds the chip design. For decades, the industry made their masks out of fused silica, pure silicon dioxide glass. The industry preferred fused silica for this because it handles big temperature changes very well. If the temperature moves by 1 degree Celsius, the glass's structure will only shift by about 0.00005%. So, if the chip pattern sitting on this fused silica plate is made up of lines about 50 millimeters wide, remember the mask's features will shrink so it doesn't have to be as small as what's on the chip, then 1 degree Celsius of variation will cause it to distort by only about 25 nanometers. Acceptable. 157 nanometers is the last wavelength for which fused silica remains transparent, and as it turns out, even the normal version absorbs 157 nanometer light. ASML and Corning had to develop what is called a dehydrated fused silica that allowed just 85% of the UV light to pass through. Using other materials to make the mask, like the crystalline calcium fluoride used for the optical lenses, was not viable because those materials would greatly warp and distort during the wafer exposure stage. So, the dehydrated fused silica invention was a critical breakthrough, allowing 157 masks to move forward. By 2002, ASML was still figuring out how to produce a suitable pellicle, which is kind of like a protective sheath, to protect the mask from contaminants, but the component looked on track for mass production. If you recall, the resist is meant to help hold the chip pattern onto the wafer by absorbing UV light from the mask. The biggest challenges here were chemical ones. Conventional resist used for 248 and 193 were basically modified hydrocarbons, but hydrocarbons at their conventional thicknesses absorbed too much 157 nanometer light. So, you either made the resist layer thinner, about 60 or 90 nanometers, which had accuracy consequences, or find something else. Some of these newer materials were very exotic and were synthesized from known carcinogens. But more importantly, it seemed unlikely that the industry would be able to formulate and commercialize a proper resist alternative in time for the 90/100 nanometer process node generation. They would just have to make the resist thinner. And that was where progress was when 157 ended. The teams developing 157 nanometer lithography managed to overcome many of these daunting technical challenges. In the end, however, they failed a more fundamental challenge. In the early 2000s, 193 nanometer immersion, or 193i technology, rapidly emerged as a legitimate next-generation candidate to succeed 193. Immersion lithography involves sending UV rays through an immersion fluid in order to improve the machine's printing resolution. The industry suddenly found itself trying to support three viable next-generation lithography technologies, 193i, 157, and EUV. There were too many options. Semitech, North America Semiconductor Industry Collective, called in the leading representatives for each of the three technologies to defend their approach in a Shark Tank-style bake-off. 157 emerged as the weakest link. It was conservative, but not as conservative as 193i, which didn't require as much new technology. And crucially, a commercially suitable 157 immersion fluid had not yet been found, while for 193i, you can use simple ultra-pure water. And while 157 nanometer technology was coming along, it was not coming along fast enough to roll out by the 100 nanometer process node. Crucially, yields on acceptable amounts of crystal calcium fluoride for the lens were still in the 1% range. And finally, there was the cost factor. Lithography machines represent over half of the total capital costs of a fab. 157 nanometer machines were estimated to cost twice as much as their 193 nanometer counterparts, a really hard pill to swallow. In May 2003, Intel, one of the technology's original champions, announced that they were dropping 157 out of their roadmap. They cited technical factors for their decision, not economic ones. The industry lurched on a little bit longer after that massive blow. They still held the 4th annual International Symposium on 157 nanometer lithography in Yokohama that August, for instance, and ASML shipped their prototype Microscan 7 to their test customer and frequent collaborator IMEC in September 2003. But within a year of Intel's big announcement, the other semiconductor manufacturers also halted their development on 157 technologies. Suppliers of lithography tools, optical materials, photoresists, anti-reflection coatings, pellicles, masks, mask blanks, metrology tools, and inspection tools. Those guys had collectively invested hundreds of millions of dollars into developing 157 nanometer lithography technologies, now flushed down the toilet. The industry pivoted to 193i in the short term and EUV in the long term. ASML released its first immersion lithography twin scan in 2006. Optical lithography gave the semiconductor industry its golden years, and the industry tried to give the technology its one last ride with 157 nanometers. But in the end, the train had reached its final destination, and it was time to move on. The lithography industry would from then on focus solely on bringing EUV to market, and the foundries would try to tread water until it arrived. Alright everyone, that's it for tonight. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.